the course in general, little information. Okay, let me go to me 2000N. So if, as many of you already have seen, or if you didn't see, I have uploaded a few more information about the oblique. If you go to for listening, not here, but in exercises here you have the preparation for the oblique, which is the questions. I prepare, I think 43 maybe questions, which are possible questions which will appear in your oblique. So the oblique will work in the following way. You're going to Canvas in the part which is called tester, and here you have the oblique. I'm not sure now it works. When you click there are some rules. So you have 6 questions. For getting the oblique approved, you need to have all the 6 answers correct. You have 2 days to finish the oblique. You can try only 1 time per session, and I will explain better what it is. And what happens is that Canvas will pick 6 of the questions that I already prepared in the list that you have in that file that is called preparation for the Obgave, for the oblique one. So Canvas already have recorded or registered the number of the question. It will pick randomly 6, too easy, too medium, and too difficult. And it will, every time that you will start the exam, then you will get given 6 questions. And from that moment, we'll start a timer, which probably will keep up open your oblique for 2 days. Again, this today is been done because in order to discourage to copy, although again, copying is possible also in 2 days, so it's not, it's just a way to make it also for me to set some precise dates, and then I can just correct all the obliques after a certain date. So my idea was the following. In this week, from this week, you have to start to think about preparing yourself for the oblique one and do the oblique one. So this one, this week, as you can see here, is written from 24 August to 29. Is the session, is the first session for doing the oblique. So you have time to open the oblique any day in this week. And then whenever you start the test, you should have 2 days. After you finish the oblique, then you have to upload the file, and then you close the oblique. I'm not sure how is the procedure on your side. I hope everything will go smooth. If there is any problem, just contact me. What will happen? I think I can actually click here. Okay, this is what will happen. So you will have all the rules here. As you can see, there is a timer here on the right side. And as you can see, Canvas has chosen for me in this case, question 17, question 25, question 33, question 35, question 40, and question 38. So you take the file of preparation for the oblique, you can print it or whatever, and you're going to look about what is this question, what is this question, and what is this question, and you're going to solve them. You don't need to upload one file for each question. You can just upload all the answer in maybe in the last question or whatever question here. So you can, for example, write on paper all the answer, scan it scan it in some way, and then upload it here in the last maybe question. So again, you don't need to upload the answer for each question. So you don't have to create one PDF for each question. If you want, you can, but I think it's just time consuming. You can just prepare one file PDF and then upload it maybe in the 6th question, and then it's okay. Yeah, so if you decide to write, you're free to decide to write the oblique on paper or on your pad or with the computer, whatever you want. Is not a big deal for me. The main thing is that if you write it on paper in your hand, with your hand, I mean handwriting, and also or with your tablet and writing. I'm sorry, if you write it on paper and writing, then you must scan it with the printer in the university. In the past, I have seen some people that they have tried to scan it with a mobile phone. The quality is very bad. It depends on the mobile phone, of course. So definitely, if you try to do it with your handwriting, then scan it with the printer in the university. Do not do the camera on your mobile phone. I do not suggest that unless you have a very good camera in the mobile phone. And if I don't understand some of the answer that you give in this oblique, I will ask you, probably I will contact you on Zoom or whatever, and I will ask you to show me what is the procedure. So the procedure of each that you use to solve each question should be very clear. The more comment you put on the answer of the oblique, the better it is, because it shows me that you understood the procedure. Of course, should not be an essay, so it should not be very, very long. But again, try to put as much information as it is necessary for me to understand what you wrote and if you understood the procedure or not. Okay, and again, if for me is if I have some suspicions of cheating, or if I have some something that for handwriting I don't understand, then I will contact you and or ask you in Zoom or whatever, or maybe I come even into class, and after the class I will ask you the question orally, and I will ask you to explain the answer that you gave. Yeah, so I think except this, I don't have any other information about this oblique here. There is also another things. If you go to our home page here, click here, and then
Short question, Luca.
yeah.
If you have some wrong answers, what then?
If you have wrong answer, again, as I said, for this oblique, the first one also, especially the first one, then the other I will check case by case. For this one, you need 6 by 6 answer correct. So if you do one wrong, then you have to repeat the oblique. And repeating the oblique means that, I mean, it doesn't mean that you fail and you cannot do the written exam. You can repeat the oblique the next section. And I suppose that each session will be maybe every 2 weeks, maybe. There will be a session every 2 weeks. So every 2 weeks, I will open this oblique thing, and you can repeat it. But you have one, and in theory, I set Canvas to allow you to do one try per session. So in theory that should work, but I'm not sure if it really work. I didn't test it, so then you will let me know.
Luca?
Yeah.
When is the next oblique?
The next oblique will come out in 2 weeks. So I suppose in 2 weeks you will have the next oblique and so on. So I hope that most of you have already finished or started to write, to study the digital part, because now you will have a series of obliques one after the other one. So
but you will publish the preparation for oblique 2
yes.
Next week?
No, I will do it probably today or tomorrow. So
Okay.
you have sufficient time to prepare and so on.
Okay.
I already started to write it and I almost finished it, so it should be ready soon. As I was saying before, here in exercises, I also upload another file here, solve the exercise for pre-oblique 1. You can, I clicked the wrong one. This one open for me the PDF. You can click here, and you have some exercise that I've solved for you with the minimum number of comments. I want to prepare a video, but I didn't have time, unfortunately. I hope that this one is sufficiently explained for you to understand how these exercises have been solved. So are similar exercise to what you will find oblique, are similar exercise that you have in preparation to the oblique 1. So I hope that this one should be sufficient. The only one that I didn't finish it is this one here, that one with Tinkercad, because Tinkercad you have done in the lab, so I think I don't need to show you again how to do it. But if you want to design the circuit in CD4007, the only part that I show here is to try to understand which pin I have to use of the CD4007 to build the circuit. So what I did is just assign each terminal of the transistor to a pin of the CD4007. This is the most difficult part, actually. In your case, of course, in the oblique, you also have to do the Tinkercad if it's required, if it's asked. In this case, again, I did not show because you know the procedure how to use Tinkercad because the lab one. Yes, so I think you have some example on how to solve them. So this is solve exercises. I will also do the same for the preparation for the oblique 2, which will be soon available here. You will find all the 40 or 50 or whatever question here, and then you will find some solved exercise aside. Again, the suggestion is if you the more exercise you do in the preparation for the oblique, the easier will be your oblique, the actual oblique, because if you have done the exercise before, then it's much more probable that some of the question you have done will come out. So it's up to you. You can also, if you think you don't need a preparation, you don't do the exercise and you just wait the oblique that it come out. Okay, so this is all the information about the oblique. I think it's all the information. If you have any question, feel free to ask now. Otherwise, we start with the lecture.
Will you publish the solved exercises for oblique 2 at the same time you publish the preparation?
Can you repeat, sorry?
Will you publish the solved exercises for oblique 2 at the same time that you publish the preparation for oblique 2?
Probably I will publish before the preparation of the oblique 2, and then I will need maybe another day to also prepare the other PDF with the solved exercise. Yeah.
Okay, thank you.
Okay, so then I think I provided you all the information about the oblique. So you have this week for delivering the oblique 1. Feel free to start it maybe whenever you want in along this week. I'm not sure if it will really work as it was planned. I didn't test it. I'm not sure how to test it on my side, but just try. If there is any problem, then I will look into to fix it, and then if there is any other issue, then I can change also the mode to do this oblique. Last year, based on my experience, just to conclude this, last year the point was that who was not able to complete the oblique was asked to do an oral test with me, and based on the feedback of the students, it seems that this oral test was kind of like challenging, but it seems that it was working. They felt that it was useful. So if this modality, this mode of setting the oblique here in Canvas with random question doesn't work, I may then shift into the oral oblique. So I will set some days where you can contact me, and then I can ask you some questions, some 6 random questions about the topic and so on. But let's hope that this Canvas works, because I also know that some of you are a little stressed when you do oral questions and so on. So I try to not do it, but again, we will see. Okay, so let's start with the lecture. Today, finally, we start with something related to, let me stop share. Okay, we start with the real electronic system course, microelectronic, which, I mean, what we have done is also microelectronic, but we have reviewed a few concepts about something you should know about digital technique and elektrische Kretzer. Today we are going to start probably something new. Let me share it. Where is it? Share it here. Okay, I think you should be able now for the moment to see the slide. So I will start. Okay, so from this lecture, I'm going to introduce you the electronic systems structure. So how are designed and what are the main part of electronic systems, modern electronic systems. We are going to talk a little about acquisition systems and control systems, and I will give you a brief overview about these two type of the devices. Okay, so in this course, as I told you before, you are going to learn how to design power supply, amplifier, sensor interfaces, filters, and so on. All of these parts, they are, again, uh, all of these devices are part of the acquisition system and control system. So it's very important also to know the distinction or the difference between analog and digital electronic systems, because these one are the two main categories, the two main groups of electronic devices that exist nowadays. What is an analog system? An analog system is a device or a circuit which operate or work with analog signals. So the question actually is, what is an analog signal? An analog signal is a signal which change continuously in time, and is, in other words, this means that you can represent an analog signal with a continuous function, a mathematical function, okay? So in the left side, you have the example of a continuous analog signal, because you can see that this signal is represented by a continuous curve. In the right side, instead, he is represented a not analog signal, because as you can see, there is in this point here, maybe I can use the pointer here. In this point here, there is a discontinuity. So the signal suddenly from here drop to another value, okay? Whenever you have a discontinuity, then that is not an analog signal. The signal has to be continuous here. Okay, so as you know, there are different type of signals. Most of it, they can be considered analog, like you know, there is the sine wave, there is the ramp, there is the triangular signal. Notice the difference between the triangular and the ramp. The triangular is a symmetric signal. So there is the time that is going up is the same of the time that is going down. Maybe in the picture is not well represented, but this is what is a triangular signal. A ramp instead has a very long time to go up and very short time to go down. Square wave, you can think about them as analog signal if you assume that the transition here from high voltage to low voltage happening in a finite amount of time. If instead you assume that this is an ideal square wave, then this is not an analog signal, because the voltage from 5 volt, for example, dropped immediately from 0 volt. So a real square wave is an analog signal because it takes a little time to go from 5 to 0. An ideal square wave, is not an analog signal, okay? Then when you talk about a square wave, actually, is kind of like a particular situation or a special situation of a pulse wave. A pulse wave is practically a signal which has a very small time where the signal is high and very long time where the signal is low, or vice versa. So it can have long time where it's high and small time where it's low. But the point is that a pulse wave has a different time to be high and a different time to be low. While instead a square wave is a pulse wave which has the same time for being high and the same time for being low. Someone of you asked to upload the PowerPoint. If that is a common request, then I can do it now, but otherwise I will do it at the middle of, okay, then I will just take 1 minute for doing that one. So, I will put it now on canvas. See that for listening.
It's so much easier to do notes during the class.
Okay, yeah. It's good that you made it. You let me know, so I at least do it, and also for the next time I can do it too. Okay, for listening, yeah. Usually I prepare the PDF, but this time I don't have the PDF ready, but I uploaded a PPT. So if you go in Canvas, Filler, then you go to microelectronic, then you go electronic circuit design, and then you go to for listening me 2020. You find now there the PPT for listening 4. I hope you find it. Whenever someone find it, please let me know. Okay, so I continue. Then let me open the chat too if someone, okay. So we say that the square wave is a special situation of a pulse wave, and there is a particular parameter that classifies the pulse waves, which is the duty cycle. The duty cycle is the ratio between the time that the signal is high divided by the period of the pulse wave multiplied for 100. So you understand that the duty cycle usually is one parameter that is measured in percentage, okay? Now, based on this very short definition, you understand that because the time that is in the square wave, the time that is high is equal to the time that is low, it means that the time that is high is equal half of t. So it's half of the period. So if you put half of t here in these formulas here, then you get 1 divided by 2 times 100, which means 50. So the duty cycle for a square wave is 50%. Okay. Let me take this. Okay. So normal modern electronic system, they have both analog and digital part. So for this reason, they're called analog mixed digital electronic systems. And the most common type of analog mixed digital electronic systems are called acquisition system and control system. And now I will go to explain what are they. This is the example of an acquisition system. In an acquisition system, what happens is that you have usually, you want to acquire information about physical quantity, and then you want to process this information and maybe display the information. For example, an example of a acquisition system could be, for example, a digital thermometer or an electronic thermometer, where you have a sensor where measure the temperature, and then you have electronic circuitry which adapt to the signal that come from the sensor. Then you have an analog to digital converter which transform the analog signal to digital, and then you have a computer where you can visualize actually the temperature. Okay. This is the typical and general block diagram for any type of acquisition system. You can acquire pressure, humidity, temperature, gas concentration, or whatever. But this is the 5 main blocks that, or let's say 4, because the first one is just a physical quantity, so it represents just the physical quantity. So these are the main 4 blocks that represent an acquisition system. Again, a control system is slightly different, because a control system measure a quantity, okay, and then also perform an action to modify the state of the environment. To clarify this statement, I just bring an example, the thermostat. So whenever you want, let's say that in your room there is 20 degrees, you want to change it to 30. So what you do, you push some button on the thermostat and you set it to 30. So what happens is that the system will start to turn on a heater, which increase the temperature. And the thermostat will understand when to stop, because it's also measuring at the same time the temperature with a sensor. Okay, so it's measuring the temperature, and it's also heating up the room. Okay, so in this particular case, this is the main difference with the previous system, which is the acquisition system. The main difference is that a control system do also an action to change the state of the environment. In this case, the state is the temperature. Okay, so the control system do a control. It's controlling the system. The acquisition system instead acquire only data, okay, and maybe visualize it. This is the main difference. Many people actually nowadays say that many electronic systems are nowadays digital. So then this course should make no sense, because in this course we are going to study analog circuitry mainly. So the point is that it's not true that all of the modern electronic devices are digital. Most of them, they are still analog, and cannot be otherwise. For example, sensor interface, power electronics, neuromorphic systems. These are systems, just a few examples of electronic system that must be analog, cannot be digital. Here, an example of sensor interface you can have here. You can see there is an ultrasound transducer. This is following all the circuitry that you need for reading out the electric signal generated by the transducer, and then provide the signal maybe to the computer or whatever, maybe before to an analog to digital converter and then to a computer. Okay. So this is all analog. This is amplifier, capacitance, resistance. This is all analog. This is another example, as I said before, power electronics. This is a DC-DC converter, which is called the boost converter in particular in this case, made of passive components, inductance, capacitance, diodes, and so on. This is an analog circuit also here. You can find a DC-DC circuit is very, there are many types, of course, but is the type of converter that is implemented in your charger of your laptop. So the charger of your laptop has analog circuitry inside. And finally, something I'm working recently is neuromorphic systems, which are electric circuit which mimics the behavior of the brain. So there have been some attempted of digital electronic engineer to create circuit that behave like neurons and synapses, which are part of the brain. However, they find out that with digital circuit, you cannot really actually create, mimic or copy the behavior of the brain in a precise way. Only analog electronic can do that. So that's why there is a lot of research now about this field in analog electronic. Okay, so my point is that everything in the world nowadays is analog. So everything in the world is analog. Temperature is an analog signal. All the physical quantity in the world, temperature, humidity, whatever, they are all analog signal. So you understand that to measure analog signal, you need an analog circuit. You cannot do it digital. For this reason, analog circuit are always needed to be designed. So why it looks like that everything is digital, or why many people they say that everything is digital? This is because it has many advantages to transform the system in digital. For example, the design is simple. You use logic gates. You use very few components, like a few transistors. The device can be very small, and so on. So for this reason, what happened is that you have the physical quantity that you want to measure, like the temperature. You have a sensor that measured the temperature, for example. Then you follow the analog circuitry, which read out the sensor. And then usually you transform it in digital. Nowadays, most of engineers, they try to reduce this analog part. So try to put the analog digital converter as soon as possible. So they transform the problem in digital, right? Because then, as I said before, digital has much more, many advantages. However, as I just said, there is no way that you can remove the analog part. You can make it smaller, but you cannot remove it at all. Because again, the interface, the sensor generate an analog signal. Yes, so, and also another reason why people, they try to make it smaller, the analog part, is because many people, as I said, digital is much easier to design than analog. So, but analog give you a more precise signal, okay? Remember that when you transform a signal from analog to digital, you are doing an approximation. When you transform a voltage electrical signal into bit, you are doing an approximation. So you are trying to approximate the signal with a bunch of bits, a finite number of bits. This introduces an error. Therefore, analog signal are usually preferred. And this example that I just said is very common, and some of you maybe already know about this, why analog is better. If some of you work with music or whatever, usually you prefer always analog devices for reproducing your music. If you play guitar, in the past many, and also nowadays many amplifier, they implement analog circuitry, not digital. Although nowadays most of commercial they are digital, but the very high quality amplifiers, or at least those people that really like guitar and they are very close to this sound field, they want analog circuitry because it reproduce. They say that it has better quality. Okay. Okay. So one last thing before to proceed to show you again how much is important to know analog circuitry is the following. I will show you that even to, and I also just talked to you about that even to design digital circuitry at physical level, so when you want to design digital circuitry with transistor, you need to know anyway analog theory, analog signals. As I showed you before in one of the previous class, someone of you asked me why in one of the exercises that I solved in class, there were two transistors, one PMOS and an MOS in parallel, because at the very first sight, it doesn't make sense because it was just sufficient one. But there is a reason why there were two transistors in parallel, and this one I could explain only if I can explain you the analog behavior of the transistor. This means that to design digital circuit, I need to know analog theory, which means that the digital circuit is practically analog. So you will understand this statement better later on, but this is very important. And if you will go to design ASIC in your future, you will really understand very well this. So yeah, let's proceed here. Okay, so now I'm going a little more in detail about to study each block of this acquisition system. I'm focusing on the acquisition system mainly, but I will also then talk a little about analog to digital converter and drivers, which are part of usually of the control system. But I'm taking as reference this acquisition system here shown. Okay, so let's have a look about what is inside of an acquisition system very fast. We have a sensor, which is the first block, right? Sensor is a device which transforms a physical quantity, which is temperature, humidity, or pressure, into an electrical signal, for example, a voltage, current, resistance, or a capacitance. Again, I wanted to emphasize here that the sensor transforms a variation in physical quantity into a variation of electrical quantity. So if the temperature change, you will have a variation in voltage. If the humidity change, for example, you have a variation in current, and so on. So you can have also a variation in resistance, a variation in capacitance. Another way to see a sensor, okay? I mean, from this definition, it seems that the sensor should create an electrical signal. This is not true. And this is explained by this second definition, which say that a sensor is a device which electrical parameters are affected by a physical quantity in the surrounding environment. So what is required to an electronic sensor is only that the sensor should change one of its electrical parameters, okay? So if the electrical parameter is a voltage, then okay, it generates a signal. If the electrical parameter is a current, then the sensor will generate a current. But the electrical parameter could be also its own resistance. So the resistance of the sensor or the resistance of the capacitance of the sensor, okay? So the physical quantity like temperature, humidity, pressure can change, will affect the sensor, and the sensor will respond depend on how it is built. So it can generate a voltage, it can generate a current, it can change just the resistance of the sensor, and so on. So not necessarily it has to generate a signal. Okay, then there are different type of sensor. Let's start from the simplest one and the one that is easy to understand for everyone, which is the temperature sensor. In this case, I'm showing you an example of temperature resistive sensor, which is called PT100. It's very common, so maybe some of you already have worked with it. A PT100 is a sensor made in platinum, which is 100 ohm when is 0 degree or 20, I don't remember, but anyway, it has 100 ohm at a reference temperature, and the resistance change if the temperature change. This is the package, and you can see that there is a relation between the temperature and the resistance. In this plot, it looks like a linear relation, which means it is a straight line, although you can see I think it's slightly curved, so it is approximately a linear relation, but not precisely. This is another example of sensor, LM35, where instead this sensor here generate a voltage. Okay, so depend on the temperature, this sensor generate a voltage. So this one is to show you that exists some sensor that change resistance. So they do not create any signal, they change their own resistance. And this one instead create a signal, which is a voltage signal. So there is also other type of sensor like capacitive sensors. The common example of capacitive sensor is a touch screen. I wanted to put a picture here, probably I forgot, but a touch screen is the most common nowadays example of capacitive sensor. So you just put your finger close to the display, and then the capacitance between your finger and an electrode or a conductive material inside of the display will change. So if this capacitance change, then the charge across this capacitance change, then the voltage also will change. And you create a signal that change. So you understand that we can classify the sensor in different way. We can classify sensor depend on which electrical parameter of the sensor change depend on the physical quantity. For example, you can say that there are resistive sensor. In this case, the resistance of the device change depend on the physical quantity. Capacitive sensor, it means that the sensor changes capacitance when the physical quantity change. Inductive sensor means that the inductance of the device, of the sensor change when the physical quantity in the environment change. Piezoelectric sensor are a particular type of sensor which create a charge across the device, across the sensor when the physical quantity change. Okay. On the other hand, you can also classify sensor in terms of which physical quantity they are going to measure. Okay. In this case, you can talk about the light sensor, which means that you're measuring light. Temperature sensor, which means you're measuring the temperature. Pressure sensor, which measure pressure, and so on. And gas sensor, which measure concentration of gas. Here, this is an example of ultrasound sensor, for example, which practically generate an ultrasound wave. The ultrasound wave hit the obstacle and then it come back and then is sensed by another sensor here. So the time that it takes from going from the transmitting transducer to the obstacle, let's call it T1, and then you have another time that the wave go back and reach the receiver, which you can call it T2. And if you know the speed of the sound, right, which I don't remember very well, but I remember is 1,500 in water, 1,500 meter per second in water, I think, and maybe 340 meter per second in air. If you know this speed, which is known, then you can do speed times time, and then you take space, right? This is from physics. Space is equal velocity times time. So if you know the velocity and if you know the time that it takes for the wave to go back and forward, then you know how much is the distance from this obstacle and the transducer, okay? This is an example of gas sensor. There should have been a video. Unfortunately, I don't know why here. I have always a problem to make it run. Let me see if I can fix it here. Screen wise, no pointer. No, okay, it's not really important. It's just for you, but probably if you have the PPT, you can see it. So what happened here is that you have a lamp, you have a battery, so there is a current flowing here. This is a gas sensor. The current passes through the gas sensor because this gas sensor has a certain resistance. So the current pass through. However, if there is some gas here, some gas molecules can react on the electrons inside of the sensor. So the electrons start to be busy to talk with the gas, okay, to chat a little with the gas, so they are not able anymore to bring the current. So it means that less current will pass when the gas is here. In other words, with this simple example, I want to say that the gas concentration in environment can modify the resistance of this gas sensor here. So this is the typical situation that happens in gas sensor. Problem with the sensor. What is the main problem of the sensor? The main problem of the sensor is that they produce a very small variation, which means that the electrical parameter that change depend on the physical quantity change very little. Let's say, for example, you have a sensor which generates a voltage. This means that the voltage that is generated by the sensor is very small. We talk about microvolt or millivolt. Instead, if we consider a sensor that generates current, then we are talking about picoampere or nanoampere or microampere. It's very, very small. So you understand that the circuitry that follow need to be very, very precise to work with this kind of signals. So this is not very convenient. Is a very big issue, okay? And another reason why this is a very big issue is because when the amplitude of the signal is very small, become comparable with other signals which should not be in the circuit, which are called electrical noise, okay? So if the signal generated by the sensor is very small, become comparable with the noise, and then you cannot distinguish them anymore. You cannot say this is the signal, this is the noise, okay? This is an example. For example, you can see in the left, you can have a sinusoidal signal, maybe generated by our sensor, okay? Where there is some noise over, but the noise is pretty small compared to the amplitude of the signal. So you can still understand that this one is a sinusoidal signal, right? On the right side, instead, you have that the noise is much larger and overlap to the sinusoidal signal of the sensor. And it starts to be kind of challenging now to understand that this is really a sinusoidal signal. You can see that it's going up and down almost equal to the sinusoidal signal, but could be very well a triangular wave, right? So you cannot know actually what is very well the shape. So noise, when the noise become comparable with the amplitude of your signal, this is a problem. Okay, this is my point. Okay, so how to solve this problem? So how do we improve the quality of our of the signal generated by the transducer? We need another circuitry that follow the transducer, which is called signal conditioning. Okay, in the signal conditioning, uh, usually we are going to implement amplifiers, filters, and another circuit which is called range matching. Okay, so the purpose of the signal conditioning part is to modify the signal coming from the sensor, generated by the sensor, and modified in order that become easy to work with it, okay? So to do that, we need an amplifiers, which make the signal from the sensor larger. We need a filter, which remove the noise on the signal. And then we need a range matching, which adapt the range of the output of the sensor with what follow in the system. The range matching, probably you may need more information to understand what it is. I will give it to you very soon. So don't worry if at the moment you don't understand what it is. But I hope that amplifiers and filtering purposes are very clear. So let's have a look about the first part of this signal conditioning, what it should be. Here we have the sensor as we saw before. We have a signal generated by the sensor. We need an amplifier to make the signal from the sensor bigger, larger, right? And this is called amplification, okay? In Norwegian, this one is forsterker. And we need here to amplify the signal. In order that maybe the analog to digital converter can then process the signal better and easier, okay? It is anyway, the reason why we use amplification and why we make it larger is very easy to understand. Think about when you work with something very small. It's very difficult, right, to manipulate something very small, but it's larger, then it's much easier to work with it, okay? It's the same principle also in electronic circuit. Then filtering. The signal that is generated by the sensor could be affected or in some way corrupted by the noise generated by the environment. We will talk more about that, but again, your radio, other electronic device, they generate all electromagnetic waves. And if electromagnetic waves coupled with an electronic device, it introduces noise in that circuit. So in this case, I'm calling noise ENV, which means environment noise, and could be due to radio or other electronic device. And this electronic device, you can see, introduce some little noise in my signal. So I need a filter to remove this noise so I can then have a more smooth signal. And then of course I need to amplify the signal, right, with the amplifier. So usually we need always a filter between the sensor and the amplifier. However, I will teach you in this course that even electrical component and electronic circuit on your circuit will generate noise, are source of noise. So you can understand that here at the output of the amplifier, the signal, yes, is amplified, but there is also a little noise also here, okay, which is generated by the amplifier itself. And we will study better what is the reason. So for this reason, we need a filter which follow the amplifier in order to clean again, to remove the noise which is introduced by the amplifier. Okay, so then the range matching circuit. So with this example, I hope that you will understand better what is this device. Let's consider this example here in this slide here. You have the sensor, filter, amplifier, and filter, and then the output signal of the filter is a signal between -5 and 5. You want then convert this signal with an analog to digital converter, but the analog digital converter accept only signal between 5 and 0 again. You know that the signal in a circuit, in a block, could be only between the power supply. So the analog to digital converter power supply is 0.5. So the input of the analog to digital converter cannot go negative or cannot be larger than 5. So I cannot connect the filter directly to the analog to digital converter. This is not possible. Otherwise, the analog to digital converter will go in overflow. It means it exceeds its range, okay? Will not be able to convert the signal. For this reason, we need a block in between, which transform this signal here, keep the same shape, but just compress it and shift it inside of 0.5 range, okay? So this signal here, which is generated by the filter, which will be compressed and then shifted in order that will be between 0 and 5. And this task is performed by this matching range circuit. All of these 4 blocks here, filter, amplifier, filter, matching, and let's say also the sensor, create an analog front end, or in short, AFE or AFE, or I don't know. So whenever, usually I like to say AFE, but I don't know. Whenever you hear me say AFE, then remember that I'm talking about analog front end, okay? Okay, suppose that we can take a little break, and after that I will continue with passive sensors. If you have any question, feel free to ask. We are all in the class now, and so I would like to start definitely. Okay, so let me know if someone still is not back, but maybe in the chat. Okay, so let's continue with the analog front end for passive sensors. What does it mean this? I've shown you, and we talked before about this, the analog front end, and this is the structure of the circuit for a sensor that is generating a voltage or a current, right? But what about those other sensors that do not generate voltage or current, do not generate signals, but they just change capacitance, or they change resistance or something like that? Okay, so then we have to discuss a little about that. Okay, sorry, 1 second. I need to close here the door. Okay, here I am. Okay, so the first distinction or the first things that we have to talk about is categorize again the sensor in another way. we can distinguish sensor between active sensor and passive sensor. So the active sensor are those sensors that create voltage and current signals. Passive sensor are those ones that instead change electrical properties like resistance, capacitance, inductance, etc. Here in this slide, you can see an example of active sensor. You can see LM35, which is this one here I was talking before. We're going very much back now. Here, this LM35 is a device, a sensor that generates voltage depending on the temperature. And this is active because generate a voltage, okay? So then we have also other particular type of sensor. As you saw before, okay, don't go backward now, but as you saw before, the sensor LM35 need power supply to work, okay? This makes sense because in order to generate a voltage, you need a power supply, right? Otherwise, where do you create this voltage, right? However, there are some particular type of active sensor that they do not need power supply. A very special type of sensor, for example, piezoelectric sensors, which they create voltage due to the fact that the material itself, it kind of create electrical signal. So they are made by particular material, which is called piezoelectric, which generate charge, therefore voltage, okay? So, but if the sensor is not made by particular material, then it requires power supply to generate current or voltage. And then there are also passive sensors, as I said before. Passive sensors are those ones that change just electrical parameter or electrical characteristic like resistance, capacitance, or inductance. So the problem is, I show you before that this is the system. How do I measure? How do I use passive sensor, right? What is the system for passive sensor? Well, someone can say you can use a ohmmeter, right? You can connect the ohmmeter to the sensor, and then you can just measure the resistance, for example, of the sensor and how it changes. However, although this is a good solution, but not the best, this may not work, for example, if the resistance of the sensor change fast, okay? Ohmmeter can just measure small, slow variation of resistance or slow variation of electric parameter, okay? So for the other cases, so when the variation of the resistance become very fast, then the ohmmeter cannot work anymore, does not give you the correct value. So what happened in all the other situation? So in all of this situation, when you have a passive sensor, you have to design a circuit which transform the variation in resistance or the variation of the capacitance or the variation of the inductance into variation of voltage, into variation of current. So let's consider the simple example of a resistive sensor, okay? So a sensor which changes resistance dependent on physical quantity. So what we need is, for example, to transform the variation of resistance into variation of voltage. So we need an RV converter. How do we transform a variation of resistance into variation of voltage or current, whatever? In this case, we consider voltage. Well, with the knowledge that you have from LELC, you should actually already know. It might need a little thinking, but you should know how to build the RV converter. Ole proposed the Wisdom Bridge, which is something that you did not study in LELC. So although it's a good answer, it's not the immediate question. It's not the immediate answer. Oh yeah, you did it. Okay. Okay, then that's very good. So then I will go maybe much faster here. Okay, so, but anyway, if I think about a circuit, let's say I just study electricity, just basic resistance, inductance, capacitance without Wisdom Bridge. The simplest solution that I can think about it is simple voltage divider. A simple voltage divider can be used to transform a variation in resistance into a variation of voltage. You have to start to think also simple, you understand? Don't think about something that someone teach you. Think about your knowledge and try to think about the simplest way that you can solve the problem that you have by using your knowledge, okay? And in this case, the simple solution is using a voltage divider. In fact, if you calculate the output voltage of this voltage divider here, is simply given by these formulas here. I think all of you can achieve that. If you don't, then let me know, I can calculate it. But again, it's pretty simple. So in this case, the sensor is modeled as a variable resistance, which a nominal value are 0, which is the same value of this other fixed resistance. And then it has some variation, right? Because the resistance depends on the temperature, for example. So the resistance of the sensor change depends on the temperature. And the variation is represented by this factor here. So if you calculate the voltage divider here, you get these formulas here. And so you transform a variation in resistance into variation of voltage. There is a problem of this approach, and I will show you soon with an example. I'm considering now a temperature resistive sensor with a sensitivity of 10 ohm per Celsius degree. The range temperature in my room is 050. The circuit of power supply is 5 volts, so this is 5 volt. The fixed resistor here is 200 ohm. And then what the problem asks you is to draw the plot which show the relation between the temperature and the output voltage. So first of all, you have to calculate the minimum resistance and the maximum resistance of the sensor, which is given by the sensitivity multiplied by the temperature, right? And if you use the minimum temperature, which is 0 degree, then you get the minimum resistance 0 ohm. If you use the maximum temperature 50 degree, then you get the maximum resistance 500 ohm. Sensitivity times temperature. After that, you have the value of the sensor in the minimum value and the maximum value, and you can use this value in the formulas for the voltage divider here. And you can find that the minimum voltage is 0 volt and the maximum voltage is 3.571. Now, if we are going to plot this curve here, you will get this. In particular, look about the right picture here. So you will find that this is the curve that represents the relation between temperature and Vout. Or in other words, it means that is the plot of this function here. You can see that the main problem of this sensor is that the relation between temperature and Vout is not linear. So it's not a line, but it's a curve. And I will tell you soon why this is a problem, but this is the problem. So I will tell you soon why this is a problem, but remember that analog front end have to be designed in order that the output signal has to be linearly related to the physical quantity that is measured. So the plot V out in this case and temperature should have been a line, not a curve, okay? They must be linear, okay? This is what a good analog front end requires. If the physical quantity and the electrical parameter or the output of the circuit are linearly related, this means that the physical quantity plot versus time is equal to the electrical parameter plot versus time. They are the same plot, okay? With this, what I mean, I will try to explain even better. If there is a linear relation between temperature and the output voltage of the circuit that I showed you before, for example, okay, if it was linear, then it means that when the temperature change, the output voltage change in the same way, okay? So these two curves, they are proportional, okay? So the main advantage of having a linear relation between the temperature and the output of the circuit is that if this one become double, if the temperature become double, then also the output voltage become double too, okay? If this one become 1/3, the temperature become 1/3, the output voltage become 1/3 too. So, and also the waveform here will be identical of the waveform here. Maybe in my picture is not precisely identical, but they are identical if the relation is linear, okay? So you can understand that even if you do not know in a practical situation, even if you do not know how the temperature change, if you're able to measure V out, if you're able to plot this plot here, practically it's like that you have the temperature variation, right? So by looking about the V out, you can immediately know how will be the temperature. This is why linear relation is very important, because if there is a linear relation, these two plots, they are equal, okay? The plot of the physical quantity, in this case is temperature, and the plot of the signal, electrical signal, are equal. If they are not linear, like in this case, for the resistance, so the output voltage is related by this curve with the temperature. This means that if the temperature increase, the resistance increase until a certain point. If the temperature become larger than this value here, then the resistance start to change, okay, start to decrease. If that is the case, you can see, and your real temperature in your environment is increasing, what you will read, the resistance will increase and then decrease. So by measuring the resistance, you actually cannot have an idea about what will be the temperature. You need some calculation that give you the temperature if you measure the resistance, okay? So it's not so straightforward to measure the resistance and then derive the temperature, because they are not, the plot, as you can see, is definitely different, okay? If the temperature double, the resistance does not double, okay? So there is no a simple relation between these two quantities. So it is very important again that there is a linear relation between the output of the circuit, of the analog front end, and the physical quantity you want to measure. If we go back to the voltage divider, you can see that this is not a linear relation. So the voltage divider is not very nice from this point of view. And there is another problem of the voltage divider, is due to the noise. If you have a radio here, for example, close to your voltage divider, as I told you, electromagnetic waves will go closer to your circuit and will create a noise. The noise created by electromagnetic wave can appear in two ways, in terms of voltage or current. In this case, I can show you here, there is an extra current here, which I call IN, which means current due to the noise, which is generated by the electromagnetic waves. So it's current that should not be in the circuit, but is there because the electromagnetic waves. So this current will go to flow in this resistance, and then will create, you see in the formulas, an extra term. This is the formulas that I showed before of the voltage divider without noise. And this is an extra term that appear because this current flow in this resistance here. So of course, this is something we don't want, but unfortunately, it's something that we get if we use the voltage divider thing. So what could be a better solution for this, for designing an RV converter for our sensor? A better solution is a Wisdom bridge. I think, as always say, you already have done everything about it, so I will go faster here. A Wisdom bridge is made by 4 components, and okay, someone say no. Okay, then I'm going to slow it down. Okay, I will take my time then. Then we have 4 components. We have 3 fixed resistance, which means that are not variable, and then we have 1 variable resistance. And then the main issue here when you design the circuit is, okay, what is the value of these 3 resistors here, right? Well, to make work this Wisdom bridge, you need to set these 3 resistance, these 3 fixed resistance to the same value. And I will show you which value soon. The most important thing that I wanted you to notice is that this circuit here is not something magic that someone come out in the morning one day, but it's just 2 voltage divider placed in parallel, okay? It's not something that Einstein need to come out. It is something you should be able to come out too if you think about it very well, because it's not something very complicated. They are just 2 voltage divider in parallel. and the output voltage is taken between the two voltage divider. Okay, let's have a look a little how it works. Okay, as I say before, the resistance here R1, R3, R4 are fixed resistance with the same value. Which value? The value of this resistance here should be the same of the nominal value of the sensor. What does it mean? It means that in normal situation, here, for example, we assume is a temperature sensor, right? So in a normal temperature, which means environment temperature, which let's say is 27 degree, I don't know, 25. Here I assume 300 Kelvin, for example. The value of the resistance of the sensor is called nominal value, okay? Which means the value when the situation is normal, okay? So the fixed resistance, this one here, must be equal to the nominal value of the sensor, okay? The sensor, of course, the resistance of the sensor can be written as the nominal value plus a variation which depends on the temperature. Okay, so you understand that. I substitute here the three fixed resistance with the same value, R0, 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 and they are equal to the nominal value of the sensor, here, R0. And if delta R is 0, so it means that if the sensor does not change its resistance, or it means that if the temperature is equal to the nominal value, which is 300 Kelvin, then the sensor is equal to R0, this one is R0, this one is R0, this one is R0. How much is V out in this case? Well, this is a voltage divider with two R0, one R0 here and one R0 here, which means that here is VDD half, because these are equal. And in this other branch here, you have also two equal resistance. Therefore, the voltage here in this point here is VDD half. So the voltage V out is equal the potential here minus the potential here. Here is VDD half minus VDD half is 0. Okay. So when the sensor is in the nominal situation, which means in this case 300 degree, delta R is 0, and this means that the output is 0. Now maybe I can show you the next part with the tablet, so you can follow me maybe with a calculation. I hope that probably Jorgen have done all of this calculation, hopefully. So then, can you please let me know if Jorgen have done this calculation? If he did it, I can skip them. Otherwise, I will. Okay, people asked to go through. So then I will go through the calculation. So anyone know how to derive the output voltage formulas in this circuit? So I hope you can see my screen view. No, 100% here like this. Okay, so now I'm going to draw the circuit very fast. I like to draw it like this because it's easy to see the voltage divider. This plus P out. If you don't understand what I write, please let me know, because my calligraphy is like a dog, so just it's very ugly. Okay, VDD. Let's calculate how much is V out. Okay, so V out again is equal to the difference between the electric potential VA and VB. So VA minus VB is equal V out. So now the question is, how much is the value of VA, for example? Well, VA is just here, you can see here the voltage divider, as I said before. So I hope that every one of you know the voltage divider formulas, as I say last time, is very important. I won't show how to derive it anymore. I just use it as it is. So R0 delta R, which is this resistance here, divided by the sum of the two resistance, which is R0 plus R0 plus delta R. So this is the resistance of the sensor. This is the resistance of the sensor. Oh my God, become even more ugly this year. sensor, okay. And this is instead the fixed resistance, okay? I'm talking about this right branch. Oh my God, what happened here? Okay. I'm talking about this branch here. Here I can remove this, okay. And then, how much is VB? So let's simplify even more this one here. So VDD multiply for R0 plus delta R divided by 2R0 plus delta R. I think this is basic algebra. I hope that everyone know how to do this. VB. VB is the same because now we are going on the other voltage divider here, and VB is the potential here, voltage divider, right? Here there is also no need of calculation, but I just do it for the sake of doing it. So it's the resistance over which I want to find the voltage divided by the series, which is this, because these two resistance here are equal. The two resistance in this part are equal. And so the result is VDD multiplied by R0. This is 2R0. I do all the steps so everyone can follow. VDD multiply 1 divided by 2, which is VDD divided by 2. So this is half VDD. Finally, we are going to calculate V out. V out is equal VA minus VB, which is equal, so I go to look about the formula. VDD and multiply R0 plus delta R divided by 2R0 minus VDD divided by 2. Great. Let's go to make do simplification here. We take in common VDD. Then we have R0 plus delta R divided by 2 R0 plus delta R minus 1 divided by 2. Here we take in common VDD multiply for let me see how we can take in common here. Okay, here maybe it's more convenient to do, it doesn't really matter. We can do like this. Will be a little different from the slide, but it's okay. The result will be the same, so that's not an issue. So 2R0 plus delta R minus 2R0 minus delta R. Yeah. Let me see if this is correct. 2, okay, minus 2R0, probably like this. Yes, okay. Will be a little different then. I choose another way from the slide, so at least you can see both math. Okay, so then we continue with VDD. Then here we have 2R0 plus 2 delta R minus 2R0 minus delta R divided by 2R0 plus delta R. Okay, here we can simplify this one, go away with this one, and this one, go away with one of this. And then we have VDD. Here with this symbol here, this ugly symbol, this is R. Is yeah. So please forgive me, but this is R. Yeah. Yeah. And there is no N here. Yeah. So then the result here, let me see. This is delta R divided by 2 multiplied to R0 plus delta R. Should be fine. Yeah. So let me write it even better. So we have a nicer, so 4R0 plus 2 delta R. So I hope this is very basic algebra, okay? I choose again another way in respect to the slide because at least you see I'm trying to solving with you this and I'm not copying the slide. This is something you have to know as I do it. Okay, so here you can still understand that there is a nonlinear relation between V out and delta R. So this is the variation of our sensor, and this is the output voltage. So there is still a problem here. This Wheatstone bridge seems not solving our issue. However, engineers usually say, by looking at these formulas, they say the following thing. If the variation of delta R is sufficiently small, Then we can do some simplification, okay? Now the problem is, how does it mean sufficiently small? Remember that if you write in your oblique, and this is something I did on purpose, I want to solve this one on purpose because I want to reach this point. Remember, if in your oblique or whatever you write small, big, large, whatever, or larger than whatever, you always have to put a number. This is not good. This is not what engineers do. You cannot say small because you have to say small respect to what? You always have to compare what you're saying with some real physical quantity, with one number. This is what engineers do. So here, if I just stop saying sufficiently small, this is something that engineers, they don't like it. They should not do like that. So here, in this case, I have to quantify what does it mean sufficiently small. So in my case, a simpler, very nice solution, it happened if this term here, maybe this part here in green, okay? I've written here 2 delta r. If 2 delta r is much smaller than 4r0, okay? Then what does it mean? It means that, let me write it here, V out is equal VDD times, I forgot the formulas, delta r divided by 4r0 plus 2 delta r. So if this is my hypothesis, then it means that this term here is negligible respect this, right? So this term here is negligible, so I can remove it. It is so small that compared to the other one close, it's practically it doesn't change the result in the end. So in the end, I can say that my real formula approximately is equal to VDD multiplied 4 delta R divided by 4R0. Okay. So remember that, and now you can see that there is a linear relation between delta R and V out. Why? Because let's have a look here. V out, I write it like this, is equal VDD times 4R0 multiplied 4 delta R. This one is my Y. This is a constant, which I call it M. And this is my X. So you remember this is the equation of a straight line, right? Which means that there is a linear relation between delta R, my sensor, and the output voltage, okay? And this happens, but this is important that this is true only if we say 2 delta R is much smaller than 4R0. Otherwise, this formula here is not correct, or at least it's not precise. When you write also a formula, try to make it a formula as simple as possible. So in this case, it makes more sense to write it like this: simplify here, and say that delta R should be much smaller than 2R0. Okay. If that is the case, then you can use these simple formulas here. In the, oh my God, what is this? Here. Oh my God, it's so big. What happened to this pad today? Okay, here. If this condition here is true, then you can use these simplified formulas here, okay? And now you have a linear relation. So this linear relation for the Wheatstone bridge is true only if the variation of the sensor, so the variation of the resistance of the sensor is very small. And small in this case means that the variation of the resistance of the sensor is much smaller than 2 times R0. And R0, remember, is the value of the fixed resistance in the circuit, or the nominal resistance, the nominal value of the sensor. Okay. Now, this M here, or this constant part here, is a very important role, and it's called sensitivity. This is the sensitivity of the Wheatstone bridge, and it's very important, this parameter here. And let me see. Okay, let me compare with the slide so I'll show where I am. Okay, this parameter is very important. And why I cannot go down? Okay, and it's called sensitivity. Why? Because remember that when you have a plot X and Y and you have a straight line,
let's consider a different straight line. This one is M1, this is characterized by M2, this is characterized by M3. You can see that the larger is M, the bigger is the slope of the straight line. In other words, in our case, X is delta R and Y is V out. So you understand that if M is very big, then we are happy. We are very happy because, let me draw better. That one is a little creepy. Okay, this one is less creepy. But if M is big, so if the slope of this straight line is very big, then it means that a small variation of delta R create a large variation in V out. You understand, right? So a small variation of your sensor, of your resistance, create a very large variation in the output voltage. So you want that this parameter M is as big as possible. Or in this case, for the Wheatstone bridge, for our circuit, what the heck is going on here? Why doesn't, okay, here, we want that this, okay, sorry, but I have some problem, okay. So this term here, which is the sensitivity, has to be as high as possible. And you can see for this Wheatstone bridge is not so high. We divide 4, VDD divided by 4 are 0. So it's okay, but we could find a better solution, okay? Indeed, okay, I hope that this concept, you understood it, that the sensitivity is, someone asked if I will add this to the PowerPoint. Actually, it's already in the PowerPoint. The calculation are already there. I just choose another way for solving it. But again, the result is the same. If you want, I can try to do it, but I will see. Okay, so as I was saying, the engineer found another way to improve the Wheatstone bridge. So they say, okay, how do I improve the sensitivity of the Wheatstone bridge? Again, remember the sensitivity, which is the slope of the straight lines here, must be higher as possible. How do I improve the sensitivity of the Wheatstone bridge? I just use 2 sensors, not 1, like this and like this. Let's put it where it was before. So this, so 1 here and 1 here. There is a reason why I draw them with the opposite arrow, and I will show you why. Because the bottom resistance will increase if the temperature increase, but the top resistance will decrease if the temperature increase. Okay, so yeah, maybe we can call this one RS2 and this one RS1. So if T increase, then RS1 increase. If T increase, then RS2 decrease. Okay, this is why I draw here 1 arrow that go down and 1 arrow that go up. This is the meaning. Then I go to solve again the circuit as it was before, because we don't trust anyone and we won't calculate everything by our own self. And we're going to search V out. So V out is equal, again, the procedure is still the same. We have to do VA minus VB. I will just do it everything one step. I hope it will not confuse you. If you want me to do all the steps, please let me know, because yeah. Okay, I will do for the moment with 1 step until you will tell me. So, so VA is equal to VDD multiplied for R0 plus delta R divided by R0 plus delta R plus R0 minus delta R. This is for VA minus, and in the other case, you can see that we have the fixed resistance in the left side. So it's again VDD divided by 2. I don't calculate this, pretty trivial. Okay. And then let's now go to solve it. This is even easier than before. This one go away with this. And then we're going to solve it again. VDD multiply for R0 plus delta R to R0 minus delta R minus VDD divided by 2. Let me double check if I did it correct. Of course, this one there is not there. And yes, so let's continue. So taking common VDD and also 2. So this one remain R0 plus delta R divided by R0 minus 1. And here I can simplify even more. So make everything in common. R0 plus delta R minus R0. R0 go away. And that's your result. VDD divided by 2 times, here put R0 times delta R. And once again, we get the linear relation. So this one is M, this one is the X, and this one is the Y. Straight line, linear relation, very simple, very easy, I hope. The good advantage, again, as you saw, as you can see immediately from this fast example, is that we have higher sensitivity than before, because before the sensitivity was VDD divided by 4 R0. Now we have VDD divided by 2 R0. So now the sensitivity is bigger, is larger. And again, as I said before, greater sensitivity is better for us. This is the advantage of these two sensor wisdom bridge. Another thing that I wanted you actually notice, and this is even more important than maybe the same important as linearity, is that in this case, to find a linear relationship, I did not do any assumption. So I did not assume that delta R is small, okay? I did not do that this case, okay? And this is very important because this means that this wisdom bridge with two sensors work linearly regardless if delta R is small or big or large, okay? This is very important. So if you want linearity, two resistance is the minimum that you need. Okay, finally, I won't do that. I won't do this the next step, but I hope you can do it at home. Another engineer come out with the idea, okay, then if we want to improve the sensitivity even more, then we can use 4 sensors, okay? This V out, this minus, this is up, this is down, this is down, and this is up. VDD here. And again, I won't do all the calculation. You can fill up the value here, but the result is that is VDD divided by R0 times delta R, which has even better sensitivity than the previous circuit. I hope that I show you the method for the previous 2 cases, so you should be able to actually derive this case here. It should not be difficult. And indeed, it is not. If you want me to show you, then maybe after this class or maybe another time, come to my office and then I will show you how to derive it. Another advantage of this wisdom bridge, okay, with even with one sensor, is that the noise is cancelled, and I can show you why. So I'm going back to consider like this. Only one sensor, okay, just to make it simple. As I said before, that could be some electromagnetic waves that come from wherever, no one knows, but electromagnetic waves. And it creates some current, which is current due to the noise in our circuit. Okay, so in this case, because these two branch, this branch here, this one here, and this one here are very close, it will happen most probably that the noise in the two branches is the same. Okay, so the voltage VA and the voltage VB in this situation, what will be? The voltage VA will be the voltage, the ideal value, which we calculated before, plus, unfortunately, there is a part of the noise, which is IN R0 plus delta R, which is practically the drop voltage across this resistance here, okay? How much will be VB? Will be VB ideal, which is the one that we calculated before in the previous case when there was no noise, plus there is this term IN R0, IN R0, yeah, IN R0 here, because this one is the voltage that follow here. When I do the difference to calculate V out, this one will be VA minus VB, which is equal VA ideal minus, no, let's write it plus IN R0 plus delta R minus minus VB ideal minus IN R0. So this one, let me do all this step, otherwise you may get confused. VA ideal minus VB ideal. This one represents the ideal output plus IN R0 plus IN delta R minus IN R0. This one simplify with this. So we remain just with this term here, which is something that is due to the noise. But again, when we use one resistance, we say that this term here is very small. The noise current is also small, so it makes sense that this one is practically so small that it's practically negligible. Okay, so when I say small, it means that it's small compared to the ideal value here. So as you can see, this kind of structure also is less susceptible to noise, okay? Is less affected by noise, okay? Yes, so I think now I can go back to the slide. If you have any question, please let me know. Okay, so now you should be able to see. Yeah, so this is a summary that you can find also in your slide about the Wisdom Bridge. We have 3 types: 1 sensor, 2 sensor, and 4 sensor. Here are the formulas, and you have the sensitivity is different as the number of sensor increases. The Wisdom Bridge can be used also if you have capacitance, a capacitive sensor. You can put your capacitive sensor here, and then you put in series with another capacitance, which has the value of the nominal value of the sensor. So this value here should be the same of the nominal value of the sensor. So it's the same, like, but with the capacitance, okay? Here, of course, I think it's not very good to do this because it's better to use AC voltage, actually, not constant. So I think here is an error. I have to change this voltage source symbol. So this one work with AC voltage, okay? Just to mention you what we mean with the capacitive sensor. This is a typical capacitive sensor, which is called diaphragma, and this is made in MEMS technology. It's used mainly as a pressure sensor. So we have a metal conducting material here, and we have also no, actually this one is a piezoelectric. So we have a piezoelectric material here, which, as I told you, if the piezoelectric is deformed, is mechanically deformed, then it means that there is a voltage across this material here. So the pressure, the environment pressure, or the pressure coming from somewhere, is bending this membrane. So the piezoelectric material bend, so it deform. So when it deform, then it creates voltage at the terminal of this capacitance. Okay, then you can also use piezoresistive and so on, but okay. You can also, yeah, I was talking here about, because I wanted to say capacitive sensors. There are also the sensors that have a metal conductive material here and metal conductive material here. So if this one deflect, then the distance between 2 metal change, and then you have a variation in capacitance, okay? Again, this one was just an example of sensor. There is nothing much to understand. Okay, so I wanted to do filter design today. I'm not sure actually I can start, but definitely I won't be able to finish. There is a lot of things to do, to say here, but at least I wanted to start to say something about it. And I can see. Yeah, maybe I will just introduce a little bit about it, and then we continue tomorrow. Yeah. Let me see.
Oh, maybe yes, maybe we can just do it tomorrow. It's maybe a lot of things to say. Yeah, we have still a lot of many things to say. Okay, but we can maybe stop here for today and then continue next time. Yeah, so please let me ask me question if you have, and if I went too fast in something, ask now, so I can answer you immediately. Oh yeah, I will also update the host value to week 41 if I understood correctly. So I will shift a little that is